In this video, we're going to take a look at wrapping up electron configurations. You've done the Hogg-Hilton and the electron configurations lab. Now we want to explore the patterns in the periodic table. Here's a little chemistry humor for you. So if you don't know the word degenerate, the meaning of the word degenerate clearly means poorly behaved. But also degenerate means having the same energy. So when we're talking about degenerate orbitals, we're talking about orbitals that have the same energy. So hopefully you got that one. Let's take a look at the layout of the periodic table. What you figured out from doing the lab is that the elements in the same families, remember the columns, the groups, have the very similar electron configurations. So with the alkali metals, they all end in S1. Alkaline earth metals end in S2. So each one has a particular letter and then superscript combination. And then you also found that different chunks of the periodic table all have the end in their same subshell. So S, P, D, or F, those are your subshells. And then the period number tells you the highest shell or energy level that's occupied. So remember, the periods are the rows. So that's what you want to look at. Let's look at the periodic table kind of broken out. You can see when you look at that these first two columns are the S, and as you go down the rows increase 1, 2, 3, and so on. And then this middle chunk, the transition metals, are the Ds. These ones on the right are the Ps, and then the two rows at the bottom are the Fs. So basically when I'm doing an electron configuration, hopefully you'll get comfortable doing this, you'll learn how to kind of read the periodic table across. Remember the diagonal line diagram? That is the pattern that comes from this periodic table. And when you're reading the electron configuration from the periodic table, it's as simple as going 1s, 1. If you have an element that's over here, it would end in 2p, 1, 2. So the ending would be 2p2, and we know all of the orbitals are filled up before that. So we would say 1s2 because it's filled with 2, 2s2 is filled with 2, and then 2p has 2, not 6. It just depends on where the ending is for that element. So the periodic tables that are on the wall and in your reference tables have lanthanum and actinium switched with lutetium and lawrencium. So these two elements are right here on the front, and then these two actually belong over here. So remember to pay attention to that. So if you look at the ending of the element, you can actually just kind of read straight across as you do that. The tricky things that you have to remember are the orders of the subshells, so SP, SP, and then when you add in D, it's SDP, and then when you add in F, it's SFDP. But you also have to remember that in a situation where you have a D or F subshell, you have to subtract 1 from the row number to get that coefficient for the D. So if we're in row 4, the coefficient for the D will be 3. If we're in row 5, the coefficient for the D will be 4. If we have F subshells, the coefficient for the F is always 2 less. Remember, these two rows actually belong up here, and so that's a little bit tricky. So you have to remember in row 6 to subtract 2, so that would be followed by 4F, then 5D, then 6P. So you can actually just read these across. And then you just have to remember that everything, if you find a particular element, say calcium, it ends in 4s2. Everything before that is filled up. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s with 2. All right, now let's talk about lanthanum, actinium, lutetium, and lawrencium. This is where it gets kind of tricky sometimes. They don't always fit in those nice neat blocks because of the way our periodic table looks. So you have to remember that lanthanum and actinium are in the F block, so that little two rows at the bottom. And then lutetium and lawrencium, the last two in those two rows on your periodic table, actually belong in the D block. That's a little place to get caught up. If we actually expanded the periodic table and put the F rows where they belong, you can see that we've split it here between group 2 and group 3, and we've inserted those, and you can see lanthanum and actinium here, and then lutetium and lawrencium are actually part of D. So this is your little F block here, and that's the D. You can definitely memorize the diagonal line diagram, but it is much easier if you just understand the patterns and can read the periodic table and look at those. Here's a little more chemistry humor. Look on your periodic table to see where those elements are. All right, so let's talk about gaining and losing electrons. We talked about the fact that atoms gain and lose electrons. When that happens, we call that an ion, and we express the charge, the difference in the protons and electrons, by showing that in the upper right on the symbol. And when you had the lab, the electron configuration lab in part 2, then you looked at those atoms that gained and lost electrons. So let's look at the patterns in forming ions. The patterns that show are that atoms tend to form ions that let them get to or close to a noble gas electron configuration. And that's because they're really stable. And so the atoms want to be stable. And so they'll gain or lose electrons depending on which way it's easier to go. So if you look at oxygen, it would either have to gain 2 electrons to become like neon, so hopefully you're looking at your periodic table right now, gain 2 electrons to have the same number of electrons as neon, or it would have to lose 6 to have the same number as helium. Much easier to gain 2 than it is to lose 6. So let's look at that. In alkali metals, the sodium column, that's group 1, it's easiest for those elements to lose 1 electron. With alkaline earth metals, the column that has magnesium, those tend to lose 2 electrons. Group 13, which is aluminum, the column with aluminum in it, it tends to lose 3 electrons. In group 14, the carbon group, it can go either way. And so you can lose 4 electrons or gain 4 electrons. And if I give you a question about that, I would have to tell you what happened. You can't really, you can do different, it does different things depending on the atom that it's bonding with. And we'll get into that a little bit more later when we start looking at bonding. Now in group 15 with nitrogen, it's actually easier for it to gain 3 electrons. It would have to lose 5. So it's actually easier for it to gain 3 electrons. The chalcogens, group 16, it's easier for those to gain 2 electrons. Halogens like fluorine, it's easier for those to gain 1. And then the noble gases, which are elements like neon, they don't react. They're very difficult to react because their electron configurations are so stable. They have full subshells, okay? And you want to, when you write the charges for these things, you'll see them written like this. So in this example, nitrogen, if it gains 3 electrons, remember that it has 3 more electrons, so that means it's got a 3- charge. Oxygen, if it gains 2 electrons, it would have a 2- charge. Fluorine, if it gains 1, it would have a 1- charge. And typically for that, we just write a minus. We don't write the 1. We assume that if there's not a number there, that means that there's a 1. Noble gases, they don't have a charge, so we just write their symbols. All right? So let's talk about gallium and germanium, because those were actually a little bit different. Chemistry always has exceptions. Some elements don't make it to that noble gas configuration. So gallium is actually 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. See what you can figure out there about what is different about the configuration than what you put. Look at your notes. Pause if you need to. If you notice, gallium doesn't follow that diagonal line diagram, that pattern that we looked at, because what it does is it fills the subshells that it has in order to make it more stable. Full subshells are more stable than partially filled subshells, and we'll get into that a little bit more. So you have to look at where those 2 electrons came from. You had, I'm sure when you wrote this down and did your configuration, you had all the way up through 3p6, and then you had 4s2, 3d8. And so what happened was these S2, these 2 s electrons went into 3d. So 4s is empty and 3d is now full. It just makes it more stable. Think about the meaning of the prefix pseudo. If you've ever heard of an author using a pseudonym or something like that, that is a false noble gas configuration, or you may have heard of like a pseudopod. All right, so let's take a look at the other examples. Copper, you would expect this configuration, but it actually has a 3d10 instead of 3d9. One of the s electrons moves to d. And I'm not going to expect you to know the exceptions. I just want you to see why they are the way that they are. And then chromium actually does the same thing. One of the electrons moves from S to D. Rather than giving it a full subshell, it gives it a half-full D subshell. Let's talk about the transition metal ions. It gets a little more complicated because of those d orbitals. Typically, those transition metals form +2 ions, but they can have lots of different charges. So if you ask me the charge of a transition metal like iron or copper, I'm going to say it's probably +2, but I'm not sure unless I know the formula for the compound that it's in. So I don't expect you to know that either. On the other hand, I'll be expecting you to be able to figure out the charges on all the ones that are in groups 1 and 2 and groups 13 through 18. All right? So make sure that you're working on making sure that you understand that. All right, let's talk about the stability of electron configurations. In order from most to least to most stable, the least stable configuration is a partially filled subshell. So any orbitals where all of the orbitals do not have at least 1 electron. And then a half-filled subshell would be more stable than that. So each orbital would have only 1 electron in it. And then a full subshell where there are 2 electrons in each orbital. And then the most stable would be the noble gas. So the noble gas configuration is that P6 configuration. And that just helps us to predict those charges. So let's talk about which ones I'm going to expect you to know. You can predict charges on those ions that are formed from elements that are close to the noble gases. So groups 1 and 2 and all those nonmetals groups in groups 13 through 18. And you're not really likely to be able to predict any others. So I would be able to ask you about something like calcium, but I wouldn't ask you about something like chromium. Remember that I don't know that either until you know what it's in a formula with, and we'll get into that in a couple of more units. Metals typically lose electrons, and nonmetals typically gain electrons, so that's just something to remember. The other thing we need to talk about is something called the octet rule, and hopefully you know that an octet means 8. It's in quotes because it doesn't always work, but for the most part it does. Chemistry has a lot of exceptions. You'll hear me say that, and you'll probably get irritated occasionally, but it's just part of chemistry. So the most stable ions have noble gas configurations. And if you look, see if you can figure out what might give us 8 from this configuration. Pause the video if you need to. Usually making that most stable ion leaves 8 electrons in the outermost shell. And so if you look in this example, the outermost shell is the one with the highest coefficient. And so the highest coefficient here is 5. If you add 5s and 5p, the 2 and the 6, that gives you 8. So those are the valence electrons, and you can look at any electron configuration and tell by looking at the subshells that have the highest energy level or coefficient, that those are the ones that are the valence electrons. And valence electrons, by definition, are the electrons in the outermost N shell, N being the row that it's in, 1, 2, 3, 4, 5, 6, or 7. The core electrons are any valence electrons that are any. The core electrons are any electrons that are not in that outermost shell, the non-valence electrons. Now I want you to think about this. All D and F electrons are core electrons. Pause the video and think about why that is. Okay, so let's look at this example again. If we look at the Ds, these electrons that are in the D, remember that when we go from we're in row 5 and we go to the D subshell, we always subtract 1 going from the row number, and we subtract 1, so go from 5 to 4. That means that those electrons in the D subshell are never going to be in that highest energy level because we have subtracted 1. That's why those are always going to be core electrons. So let's look at how many valence electrons each family has. Hopefully you'll notice a little pattern here. So in each family we can predict just by looking at the group number. Group 1, the alkali metals, have 1 valence electron. Think about what you might think for group 2. They have 2 valence electrons. Transition metals and the ones in the F block all have 2 valence electrons, and we'll talk about that in just a minute. Group 13 has 3 valence electrons, so all the elements in that column with aluminum have 3 valence electrons. Group 14 has 4 valence electrons. Group 15 has 5. I hope you're seeing a pattern here. Group 16 has 6. Group 17 has 7. Group 18 has 8. Don't forget to be working on those group names. Okay, so remember with the transition metals, what you have is the same situation that we had in the earlier slide, where you would have, say, 4s2 and then 3d5. Those 3d electrons are core electrons, so only the 4s2 electrons are valence electrons. So those ones, anytime that you're in that D block, they are only going to have 2 valence electrons. Same thing for the F block. Okay, so let's look at how to shorthand these, because I know we've written a lot of arrows and electron configurations. The core is really boring, no reactions really happen there, so what we do is we make a noble gas the core of the configuration. We leave those outermost electrons where they are. We write them just like we have because that's where the reactions occur. That's always exciting to see where the reactions occur. So let's look at some condensed electron configurations. So if you look at silicon, we typically would write that electron configuration 1s2, 2s2, 2p6, 3s2, 3p2. We want to find the previous noble gas, and we're going to take it and put the symbol in brackets in place of the electron configuration of the noble gas. For silicon, the previous noble gas is neon. Remember, previous means the one before it. Those electrons don't change. Those are core electrons. Those are the ones that are not going to react. So let's look at our electron configuration again and compare it to neon. If you notice, these parts are identical. So by putting that neon in brackets, we're taking the place of that first part of the configuration since those are core electrons. So the way that we write it is neon in brackets, the symbol for neon, and then the part that are not the core electrons, so just that 3s2, 3p2. And that's why it's really important to know those patterns. What you'll find is that you will struggle with doing these condensed electron configurations. It'll make it actually more work because you'll have to do this rather than just looking at the patterns on the periodic table and figuring it out. So let's look at a few